Hello there. Welcome to Chapter 1, or as the course says, Project 1, uh, which is Boolean logic. Let's see what this chapter or project is all about. We start with NAND gates and we build elementary chips, and we use these elementary chips to build 16-bit variants and also build multi-way variant chips. This will be the entire journey in this project. Let's look at the elementary chips. What is the project all about? Given NAND gate, we have to build the following chips. Basically, we have to build the following logics using NAND only. We have to implement NOT chip and OR multiplexer and demultiplexer. Let's get started with the first chip, which is the NOT chip. What is the logic? When the input is 0, output is 1. And when the input is 1, output is 0. The symbol used is a triangle with a circle, and you have the input and the output. Let's look at the truth table. You have the input 0 and output is 1, and when input is 1, the output is 0. And the notation used is output is input dash. Not chip basically negates your input. Whatever input you pass, it will simply flip the switch and give you the opposite of it, or the complement. Now, let's start looking at the implementation. You have a NAND gate and you have two pins. You have the A, B and output. I'm simply passing input and input for both the pins, and the output is expected to be input dash. Let's prove that this implementation here in fact gives us the NOT chip or the NOT logic. So both the pins are taking input. Output is NAND of input and input, and we know that NAND is AND combined with NAND. So you got in into in dash, and idempotent law says A into A is simply A, and you have input dash, which was the logic that we intended. So this particular implementation here gives you the NOT implementation using NAND only. Let's look at the HDL implementation. So you just say chip and you give NOT, you declare the variable input, and you declare output variable, and you have the inbuilt given NAND function. Input A is in and B is in and output is out. Later I'll do the implementation on the IDE and we'll see that this works. Okay, let's get going with the next chip, which is AND. What is AND logic? If all the inputs are 1, the output is 1. Otherwise, it is 0. Even if one of the inputs is 0, it is 0. The symbol is this. Notice there is no circle here. If you have a circle, it becomes NAND. The truth table, when you have two zeros, it's 0. And when you have two ones, it is 1. Only when both the inputs are 1, it is 1. Otherwise, it is 0. And the notation used is A dot B or simply AB. Let's look at the implementation. So we need two NAND gates here. A and B are the inputs for the first, and you get AB dash, which is fed as inputs to both the pins of second NAND gate. Now let's prove that this implementation in fact gives you the NAND logic. So NAND 1, pin 1 is A, pin 2 is B, output is AB dash. NAND 2, pin 1 and pin 2 both are AB dash, and you get AB. Because we have seen from NAND gate, whatever input you give, you just get negation of it if you pass the same value to both the pins. In the previous case, you had input and you had input dash. Here you are passing AB dash, so you get the complement of that, which is AB. And hence you have the proof there. Let's look at the HDL implementation. You have two NAND chips A and B are the inputs and output is the output variable. So input A and B variables, output is out, and the parts are two NAND gates. The first NAND gate takes A and B as input. I am considering a temporary variable as not AB, which is the output of the first NAND. I'm feeding that as input to both the chips, both the pins of second NAND gate to get the output. Let's move on to the OR chip. Logic. If one of the inputs is 1, the output is 1. Otherwise, if both the inputs are 0, then the output is 0. Let's look at the symbol. We have this symbol here and the truth table. When you have both the inputs as 0, it is 0. Otherwise, even if one of the inputs is 1, it will return 1. Notation is A plus B. Now let's look at the implementation using NAND only. So we need 3 chips here, 3 NAND chips. In NAND 1, you are passing A as input to both the pins. In NAND 2, B as input to both the pins, and use A dash and B dash as inputs to the third chip. Let's prove that this in fact gives you A plus B. NAND 1 takes A, and we have seen from NAND it returns A dash. B and B returns B dash. Feed that A dash and B dash as inputs to NAND 3. Let's simplify this. Yeah. NAND of A dash and B dash, which is A dash B dash whole dash, and using De Morgan's theorem, second law, it simply gives you A dash dash plus B dash dash, and using the double negation law, which is X dash and dash, if you take negation of anything twice, you'll get back the same value. Take 0 for example, negate it once, you get 1, negate it once more, you get 0 back. So you get A plus B, which proves that this implementation in fact gives you the OR logic. HDL implementation, A and B are the inputs, out is the output. You have 3 NAND gates in the parts. So A, B, out, NAND, you have A is A, B is A, output is not A. These are the temporary variables which will be passed to the last chip. So second gate, B and B, you got output is not B, being fed into not A and not B. Now let's move to the next chip, which is 2:1 multiplexer. Basically, a multiplexer chip acts as a selector. When you have two inputs coming, it allows you to select only one of the inputs based on a selector signal. So when the selector is 0, we choose input A. When the selector is 1, we choose input B. You can switch this, but the notation will change a little. That is the logic. Depending on the selector signal, will allow which input to pass to the output pin. The symbol is a triangle multiplexer with a selector signal, 2 inputs and selector. If the selector is 0, you get A as output. The selector is 1, you get B as output. This is the truth table. This is not something, it looks a little bit scary, but it's not. Look at the selector is 0. Whenever the selector is 0, whatever input A is, it will simply give as the output. I think I made a little mistake in the truth table. The last column is in, it should be out. So first 4 rows where the selector is 0, whatever A is, it will simply come out as output. In the next 4 samples where selector is 1, whatever B is, it will simply come as S. And the notation is A S dash plus B S. When S is 0, the first term becomes A, the second term becomes 0, which is what we want. When S becomes 1, the first term becomes 0 and the second term becomes B, which is what we want. That was multiplexer chip. Let's look at the implementation using NAND only. This looks a little complicated, but it's not. What we are trying to do is implement the AS dash plus BS. Let's prove that this in fact gives you the uh, logic that we intend to. NAND1. S is being passed as value input to both the pins, so you get S dash as we have seen from NOT chip. NAND number 2, S dash to the first pin, A to the second pin, you get A S dash whole dash. NAND number 3, pin number 1 is selector signal, pin number 2 is B, you get B S dash. NAND number 4, A S dash from NAND number 2 and A S dash whole dash from NAND number 2 and B S whole dash from NAND number 3 being fed as inputs. And as you can see, the simplification process using De Morgan's second theorem and double negation rule, we get AS dash plus BS, which is what we intended. HDL implementation. 4 NAND chips, A, B, and selector as input and output as output variable. A, B cell as inputs, output as output. NAND number 1 takes selector as input to both the pins. Output is not cell, which is a temporary variable. NAND number 2 is okay. I have changed it a little bit. NAND number 2 and 3 are interchanged. NAND number 2 takes NT cell, S dash and A as input and gives NT SL NA. And number 3 takes B as input, cell as input and gives B NAND S. Both are fed and the final output is given as plug back to output pin. We'll implement this in after DMux is done and you'll see how things work. DMux chip. Logic. Yeah, DMux acts as a splitter signal. It splits your signal into A and B. So if the selector is 0, A is input and B is 0. If the selector is 1, A is 0 and B is input. And the symbol used is this, which is MUX chip rotated 180 degrees. The truth table is pretty simple. You have the selector as 0, it will select A and B is set to 0, and whenever selector is 1, it will simply choose, it will pass input to B and A is set to 0. And the notation is, this is a 1:2 demultiplexer chip. There's one input coming being split into 2. MUX, you have 2 inputs and you're selecting, you get only one output. A is input S dash and B is input S. Let's look at the NAND implementation. You have 5 NAND chips. Let's prove that this gives you your the required implementation. NAND 1 pass S to both the pins, you get S dash. NAND 2 pass S dash and input, you get input S dash. NAND 3 pass input S dash as inputs to both the pins, you get negation of that and you get input S dash, which is A. Similarly, NAND 4 pass input and selector, you get input S dash. Pass that as input to both the pins, you get B. So we have proved that this is the case for, we have proved the NAND implementation by theory. Let's look at the HDL implementation. Yeah, this should be pretty clear by far as of now. And continuing ahead with the next chip, which is the XOR chip. Logic. The chip performs the logical operation A B dash plus A dash B. Okay. Let's look at the symbol associated. It's OR gate and you have a line, a curve before that. Truth table is this. It performs A B dash and A dash B. This will be particularly useful when we'll be building the ALU chips. The notation is AB dash plus A dash B. Let's look at the NAND implementation. You have 4 NAND chips. Let's go ahead and prove that this in fact gives us the required logic implementation. NAND 1 takes A and B as input and returns AB whole dash. And NAND 2 takes A as input and output from NAND 1 as input to give A dash plus AB. NAND 3 takes output from NAND 1 and B as input to give out B dash plus AB. And NAND 4 takes outputs from NAND 2 and NAND 3, which is A dash plus AB and B dash plus AB to return A dash B plus AB dash. You can take this as an exercise and prove it. It was a little longer, so I've decided to leave it as is. And this was the implementation of the XOR chip. This completes implementation of all the elementary chips. Let's get going with the implementation now. All right, here's the implementation. You need one NAND chip. Project number 1. First gate is NOT chip. We implement, you need only one NAND chip. Input A is in, input B is in, and output is output. That is done. Now we'll run this here. It says simulation successful. The output file is identical to the compare file. So this implementation is good. Let's get going with the second image. You have the OR implementation. No, second chip is not. Okay, you need 2 NAND chips. Go ahead and close this. So you need 2 NAND chips. Going ahead with the AND. You need 2 NAND. The first NAND takes A for pin 1 and B for pin 2. A and B. And output I'll just call not AB. Input, second NAND chip takes this input for both the pins, which is not AB, not AB, not AB, and we plug it back to output pin. Let's run this. Yes, and the simulation was successful. Let's move to the third chip, which is the OR. We need 3 NAND chips. We go ahead and write that down. We have 3 NAND chips. First NAND takes A as inputs to both the pins. Second NAND takes B as both the inputs to both the pins. So A returns not A. B returns not B. And we feed the outputs of NAND 1 and NAND 2 to NAND 3. So we feed not A, not B, now plug it back to output pin. Let's run this. And yes, there you go, simulation successful. Moving on to the MUX chip. Yes, we need 4 NAND chips. Let's implement that. First NAND takes S as input selector to both the pins, and it will give you NOT cell. Second NAND takes S dash and A. Yeah, NOT cell and A, and it will give you NOT cell and A. Third NAND takes S and B. Third NAND takes selector and B. We'll just call it NAND selector NAND B. Thus, the outputs from nand2 and nand3 are fed as inputs to nand4 to get this. Let's run this. Yes. Now let's get going with the DMux chip. Yeah. We need 5 NAND chips here. Let's do that. First NAND takes selector as inputs to both the pins, and it should return you NOT cell. Second NAND takes NOT cell and input. It's NOT cell and input, and it will give you input and NOT cell, and this is passed as input to NAND number 3 to both the pins to give you A. Output is A. NAND 4 will take input and selector, input, selector. It will give you input NAND selector, which is fed as input to both the pins. And the output is this. Let's run this. Simulation error. Where is the error? Selector, selector, input cell. Output is B. Gotten used to the convention there. Yeah, simulation was successful. Now let's implement the XOR chip. XOR takes 4 chips, 4 NAND. Let's implement that. NAND number 1 takes A and B as input. A and B, I'll just call A NAND B. And NAND number 2 takes A as input and A NAND B as input. A and B, and the output I'll just call temporary 1. NAND number 3 takes A and B as input and B as input. So A and B and D, I'll just call this temporary 2. Temp 1 and temp 2 as being fed as input to NAND 4 to get the NAND logic, XOR logic. Temp 1, temp 2, output is output. Yep, simulation successful. That was implementation of elementary chips in project number 1. In the next video, we'll be doing implementation of 16-bit variants of NAND or MUX, etc. We'll catch you there. This was end of project 1. Implementation elementary chips. Thank you.